Okay, now here's a restatement of our original problem. I don't bother saying x equals 12.3 or x equals 12.5 or whatever. I just consider y to be a function of x and write y of 12.3 equals 4.7. You can compare that with the statement of the original problem, see that it's identical. And y prime of 12.3 equals 21.6, which again says exactly the same thing as the first problem, the original problem. And our question is then, what is the best estimate of y of 12.5? So that's it. And we can say that, okay, well, again, delta x is 12.5 minus 12.3, or 0.2. So delta y is approximately equal to y prime of 12.3 times 0.2, which is approximately 4.3. So y of 12.5 is approximately 4.7 plus 4.3 equals 9.0. There's a picture that goes along with that. Here we have the point, and we can put a coordinate system on it. But I'm not going to do that. I'm just going to label the point. This point is what? This point is 12.3, 4.7. We have a segment here whose slope is equal to the derivative. So we're going to say the slope here is 21.6. So that's the slope of the segment. So if we move .2 units here, and of course that would be our delta x, then delta y along this slope segment is going to be slope times delta x, which is y prime of 12.3 times 0.2, which is, running out of room down here, but we'll try to slip it in, 21.6 times 0.2, approximately equals 4.3. So that gives us then 4.3 here. So that moving over 0.2 moves us from 12.3 to 12.5, moving up 4.3 moves us from 4.7 to 9, and we conclude that this new point here, which should be close but not exactly on the graph of our y function, should be about 12.59. And I'll add that y prime, y double prime, and that would be y double prime at 12.3, but y double prime equals negative 11.6 would imply that instead of being a straight line, our graph is concave down, meaning that this 9 was a bit of an overestimate, and that our actual graph had some sort of downward concavity, and the result being that our estimate would be reduced from 9 to 8.8.